But one of the difficulties in getting those fundamental principles is that it's very hard to see what is going on the surface of a catalyst under the conditions under which the reaction is running. And that's because there's very harsh environments at which, very harsh conditions, very harsh environments at which the reaction is taking place. And what I mean by that is there are very high pressures of gas. The methane and the water are very high pressure, maybe 1,000 atmospheres, and the temperatures are very high, 1,000 degrees centigrade. And so what our research has been directed at is trying to get at those fundamental principles, but we had to come up with some tricks to kind of simulate this high pressure, high temperature reaction under laboratory conditions where we have the tools to look at what is going on at the molecular level. But let me give you an example of a reaction where the nickel metal, which we use in our laboratory, is a catalyst. In that example, it's called the steamer forming of natural gas. And natural gas is largely methane. And steamer forming is the reaction of methane plus water to give you CO, carbon monoxide, and hydrogen. And this is a reaction that produces all of the world's hydrogen, molecular hydrogen, hydrogen that you might think about for using in a hydrogen economy, but currently hydrogen that is used in any other, as feedstock for any other chemical reaction. It's the hydrogen that you need to react with nitrogen to get ammonia which then in turn is used to make fertilizer. So this is an extremely important reaction, and it's a nickel metal surface that is the catalyst for that reaction, and you have to have that nickel metal surface there. One of the very remarkable things that we found is in the case of the steamer forming reaction with this methane molecule, what is very important is that the temperature of that methane molecule be high. And what that means is that if the temperature of the methane is high, that means that methane molecule is moving fast. So methane is this tetrahedral shape. Carbon in the center, hydrogen atoms in the four corners of the tetrahedron. And what is necessary is for that methane molecule to splat into that surface so that when it hits into that surface, it is being deformed. The hydrogens are moving back, and you get the carbon in close enough to the nickel to start to form a nickel-carbon bond. That's the key, is forming that nickel-carbon bond. Because once you form that nickel-carbon bond, you're also forming the nickel-hydrogen bond, and the formation of those two new bonds leads to cleavage of that CH bond. And that is the key, is the energy of that methane molecule. But the key here is for the chemical engineers, if you want to save some energy, and running these reactors, these steamer forming reactors at 1,000 degrees C is very energy intensive. You're pumping a lot of energy into the system, but you're heating up both the methane and the water, and you're heating up the catalyst, this nickel metal catalyst. And the bottom line is you don't have to do that. It doesn't matter what the temperature of the catalyst is. What matters is simply what the temperature of the gas is. And so by taking that piece of fundamental information, you can think about redesigning a steamer forming reactor so that you're only heating up the gas and you save all that energy in heating up the solid. So that's just an example of how some very fundamental information, knowledge, principle about how that reaction works can feed back into better and more energy efficient reactor design.